Not really pipe flow, but interesting enough, I guess related to other flows. The idea that you can make an umbrella just by having a jet of air that goes above your head and keeps all the drops of rain from hitting you on the head. I guess you have to make sure you have batteries for it to work, but I'm not sure why I put that in. I just thought it was kind of interesting at the time. What else we got? Oh yeah, a bit of death and disaster. So this was from a few years ago. I'm not sure if it says the date here. San Bruno, just near San Francisco Airport in California. Obviously, all the gas that gets supplied to us is on pipelines, talking about pipe flow. And so I guess you want to make sure that those pipes are actually have some integrity to them and they don't weaken. Everyone talks now about, instead of natural gas, the hydrogen economy. So the idea that you could generate hydrogen by electrolysis from wind power or PV cells generating electricity, split water into hydrogen and oxygen, use the hydrogen, burn the hydrogen or use it in fuel cells. And of course, then you can use all the infrastructure that's in place for natural gas, except hydrogen hydrogen has a problem of hydrogen embrittlement in that it's such a small molecule that it gets into steel and it tends to fracture it easily. And so this was an explosion, I guess, in a neighborhood of a gas pipeline, which is underground, which obviously ruptured and maybe killed a couple of people. Also thought it was interesting in State College that when there's discussion, the heating and cooling on campus is provided by coal, used to be. The steam plant at the corner of Burroughs and College. And to lower carbon footprint, and probably for cost as well, it was set up so that would be changed to being natural gas. So they took down the big stack, they put up a couple of small stacks of the natural gas, they burned natural gas in it, and it was interesting that the people who probably thought that was a good idea actually didn't want the gas pipeline to come up, perhaps up Burroughs Street or perhaps up Allen Street, because they're worried about the safety of it. I guess that's kind of echoed here. Never watch RT because I don't think it's bona fide, but you see something going on in the background. I don't know if that's a gas pipeline or not. And finally, is it finally? Oh yeah. I guess that's just a headline. And this is an animation. No, this is the animation I want to show. And so you probably have heard, certainly in your lifetime, in the recent past, it was the Biden administration who killed it. The XL pipeline, which was supposed to go through Nebraska, through the Midwest. And the idea was it was a big push by the Canadian government because in Western Canada, they have tar sands in Western Alberta, just on the east side of the Rockies. And these are kind of unconventional oils. They're it's like bitumen. It's almost like the tarmac asphalt you put on the road. It's so thick. And so to get it out of the ground, typically you use what's called SAGD. SAGD is steam-assisted gravity drainage. So it's so thick, you pump in steam, you warm up these shallow sands, probably 10 or 15 or 50 meters deep, no deeper than that. The heat reduces the viscosity of the bitumen, and so it flows by gravity under its own weight in the pore space. You gather it, and then you take it out, and then you refine it. So the XL pipeline was due to be able to take all of that oil down to the Gulf Coast, to refineries, through central U.S. And so it's relatively heavy, carbon-wise. It's called a dirty oil, I guess, in terms of its carbon footprint. High carbon to get it out, because you have to use energy to get it out, heat up water to pump in as steam, and then once you do get it out, it's quite heavy oil in terms of carbon. Methane is CH4, so 4 hydrogens to every carbon. These oils are much less. But the point is, we talked before about these oil containers, these tankers, which have flared ends, and we talked about it in the context of having them so that when you accelerate, the oil can move, or the fluid in it can move to the top, and it doesn't pop the cap off the top of the tank. And so the XL pipeline, of course, is to send oil by pipeline instead of sending it by tanker. And so the idea of that is that even though we showed exploding pipelines before, exploding pipelines are probably safer than taking it through neighborhoods by rail. And so this was a tragedy called Lac Mégantic in Quebec, a train carrying a number of cars, basically an oil train, maybe coming from the Bakken in North Dakota or Western Canada, full of tankers, which was parked outside the town of Lac Mégantic at nighttime. It wasn't secured properly. The brakes came on, did whatever, and then it ran into the town. And it killed 40 people who were actually, up late at night at the one bar in town or whatever, as it derailed. And so the theme, I guess, of our class is kind of, we're veering off it a little bit, but pipelines, they're what link up the country for hydrocarbons, for gas. When you turn your stuff on, I guess this is a picture of it the next day. No, I won't replay it. But anyway, the point is that pipelines are used in everything that we do. They're in use for the stuff that we have in our houses. They bring natural gas into houses and hospitals and buildings, etc. And so they're part of pretty much our everyday life. They're even part of the jet lev, right? The jet lev has a pump, sits on the water, the umbilical comes up into the back of the person, and then squirts down either side. That's essentially pipe flow. And of course, the essence of pipe flow is what we talked about last time. So that's kind of the intro to where we are for today. So, important in terms of what we're dealing with. Let me get set up here. Okay, all right. So, I thought we would do these things today for 10-2, since we're on schedule. Initially, just re-discuss what we've seen many times before, the Bernoulli/energy equation. So the energy equation is just the Bernoulli equation plus the the pump heads for pumping and the head losses for frictional losses. Talk about what frictional losses are. We've already talked about them a little bit. And then talk about these three things. The Moody chart, which is nothing other than the chart that we kind of alluded to before, which is the essence of pipe flow. And we'll try and get to that and talk about minor losses, which are losses within fittings, going around bends, and entry and exit losses. But I think we'll spend most of our time talking about rationalizing the energy equation. So the energy equation, I'm not sure, perhaps maybe I should draw something. So if you took a kind of a fake geometry that we might want to play around with, that involves pipe flow between two tanks, it looks something like this. And those two tanks maybe are at different water elevations. Not supposed to be sloping, right? And I guess it should connect up at the top. So this would be a point here, and then this would be a point here. We can draw our coordinate system in it. Z is always positive upwards. And I guess we could define an expression which goes from upstream side. So this is upstream, obviously, to downstream because of the water elevations. And the expression for that would be something like this. You've seen it many times. Elevation head, pressure head, velocity head, the pump head on the left-hand side is equal to Z2 plus P2 over unit weight of the fluid plus velocity squared 2 over 2g. And I suppose we could add on also the sum of the head losses. Just to remind ourselves, we've always defined pump heads in terms of something that looks like this. It's equal to probably unfortunate units, but this is rate of doing work, so this is power divided by density times volumetric flow times gravity. So these two terms together would be what we've called in the past mass flow rate, right? Density times volumetric flow rate. And we've also, although we've never really derived it, but we'll get there today, we've talked about these head losses. And we can talk about what we'll call major losses, which are defined by some parameter, a friction, not a function, friction factor, length of the pipe over its diameter, times the velocity head. And I suppose this would, for this jump, let's not draw it there. And so this would look like this, I guess. Physically, what this means is that this would be, if this was a pressure defined not as a pressure but as a head, the head loss would be the drop-in head across the pipe, and the pipe is of some length, which we'll call lowercase l, and of diameter d. And of course, v is the velocity in that pipe. So it doesn't have this term on it, because it's not that term. It's actually the velocity that would be in this pipe in which the loss occurs. And clearly, also on this, right, if you go across from here, this would also be the head loss between upstream and downstream, physically what it is. And so this is what we'll call the major losses. And just to finish it off, talk about the minor losses. And so this is a summation of all of them. And the minor losses we've already seen once before. It's this coefficient between 0 and 1, v squared over 2g. Again, the velocity within the fitting. And so this would be for things like bends in pipes. And again, this would be some defined velocity within the system. So these are the two losses that we have, and they'll always look something like this. And so when we're solving this, I guess what we could do is we could typically write this easily as 1 and 2. Those would be our locations. And so if we deal with those, the differences in elevations wouldn't cancel out. But these would be at atmospheric pressures. So this would be 0, and this would be 0. These would be big tanks, and so this would be 0, and this would be 0. And if there's no pump that's in our system, so this is 0, then the difference between the head losses are just going to be C1 minus C2 equals sum of HL. So I kind of jumped to that by drawing this, but that's exactly what this is, right? So that doesn't help us very much, because it just tells us exactly that the head loss is equal to the difference in elevation. And so if we wanted to figure out exactly what the head loss was within the system, what instead we could do, I suppose, is we could write the behavior at each of these 2 points here, and we could call those, I guess, 3 and 4. And so this one was between 1 to 2. Now if we write it 3 to 4, then I guess I could write this equation out. Well, why not? I can do it much better than that. If you're rushing to write this, I can probably, I guess it removes it from there, but I guess you don't need it. It's recorded somehow. So we could look at what these individual components are without me now writing it. I just need to change it slightly for the fact that now the suffixes wouldn't be 1, 1, 1, and 2, 2, 2, so you see exactly where we're going with this, hopefully. They would be, upstream would be 3, and downstream would be 4. Yes, I can tidy it up again and then talk about what these individual components would be. And so what do we have now? Elevations of these two, well, they're kind of on the same level, so I guess elevations would be the same. So this and this would drop out, not because they're 0, but I guess because they're the same as each other. The velocities, if it's the same diameter pipe at both ends, then these would also cancel out, because not because they're 0, but because they're the same as each other. Join here. We're assuming that there's no pump in the system, so that's 0. And now the differences between them would be that, okay, so you didn't correct me, but of course it's wrong. These should be 4s, right? And so now P3 minus P4 over unit weight is equal to the head loss. And we kind of know that from our unit conversions that the change in pressure is equal to the change in head multiplied by unit weight. We can just get that from this. Delta P, delta H, this is a delta. And so physically, really, that's what it is. If we draw the pressure as an elevation, a height of water that would rise up in a pipe above this, then this is really going from this magnitude to this magnitude downstream, and this is just the head loss. And so we can always define the head losses in terms of that. And that's the typical system that we'll deal with. You'll note, of course, that if we have Bernoulli and the head loss is 0, then there can't be a drop between these, right? We can't sustain it. And you can think of that in terms of if this, instead of being, if the viscous losses on the pipe are 0, that's like the pipe being really, really big, which is like the tank being really, really big. This, instead of being a pipe, it just being a continuation of the tank. And of course, in a single tank, you can't have 2 different elevations unless it's accelerating somehow. And so Bernoulli wouldn't allow these elevations to be different, because the essence of pipe flow is that we're losing some energy, pulling my bag along the surface as it flows from upstream to downstream, and it's these frictional losses that occur as we go from upstream to downstream. So that's it. So the essence of pipe flow is then being able to figure out exactly what these magnitudes of head losses are. And so we should spend some time maybe figuring out exactly what that means. And so the easiest way to do that is to think about we didn't really do last week, but what was on the cards for last week, which was dimensional analysis. It's dimensional analysis, but it uses dimensionless coefficients. And this just says that what we can do is we can analyze, say, flow within a pipe. And so our flow within a pipe would be defined in terms of the features of that pipe that describe the flow. And we can imagine the features would be the velocity at which the fluid flows, I suppose the pressure drop that occurs along the pipe, delta P. We've already described some of the features of it. It's a length, and it has some kind of diameter to it, internal diameter, since we're interested in flow. We said last time that we might be interested in some roughness. So roughness, well, let me draw it larger. Roughness would be epsilon, the magnitude of this, which equals roughness. Greek E, in other words, roughness. And I guess a couple of different properties of the fluid, which would be the density and the viscosity. And so what we could write from this is that the pressure drop that we have in the system is some so this is a friction factor. This is a constant. So I don't know if I can draw a squiggly F. So this is a function of. And so this is going to be a function of the density, the viscosity, maybe change colors for the other parameters, the velocity, the length, the diameter, and the roughness. So this is 1, 2, 3, 4, 5, 6, 7. So this gives us 7 terms. We know that from Buckingham pi, number of dimensionless terms is equal to, I think we call it k minus n. K are the number of terms, which are 7 in this particular case. N is the number of mass, length, or dimensions that are mentioned. I guess this could also be temperature as well. We don't have temperature in this, so we won't worry about that. So mass, well, density is mass per unit volume, so mass is certainly in there. Length, certainly in there. And velocity is meters per second, so each of these 3 are represented. So this would be equal to 7 minus 3, which is equal to 4. And so we could use Buckingham pi to get those, but let's not. Let's instead just rationalize the things that we talked about. And so if you remember last time, if I go back to this figure, we tried to make this analog between internal flow within a pipe, external flows outside a pipe, or say on a turbine blade, and open channel flows. And we said that when we solve those systems in terms of the dimensional behavior, we can define in terms of geometric, kinematic, and dynamic similitude. So geometric means the pipe model that we use in our experiments has to have the same dimensions as the real pipe. So maybe it could be a scaled model, or certainly we could use a real pipe in our calculations because it's not so big. Kinematically, the flow regime in that pipe has to be identical to the flow regime. It's not so obvious within a pipe, but we use this idea that if you flow around a sphere or a cylinder, if you flow very slowly, it's kind of a creeping flow that hugs the cylinder. If you flow much quicker, it's this flow that breaks off in the downstream portion, and you get lots of vortices. These are the vortices that give the Tacoma Narrow Bridge shedding from the top of the deck and then the bottom of the deck. Alternately, it gives it this oomph. So we want the flow regime to look exactly right, and that's done by making the Reynolds numbers equivalent. And then if we do that, we can use the Euler number, which says something about the forces that are applied on that structure. And so what we can do here is we can do that exactly, and we can look at those requirements. So in terms of geometric similitude, and let's write them all down first. Geometric similitude, kinematic similitude, and dynamic similitude. And just remember what these are. Kinematic similitude means the flow regime is the same in the model and the prototype. Dynamic similitude means that the forces applied to the model and the prototype are the same. And so we know that for dynamic similitude, we want the Euler numbers to be the same. And the Euler number we define as a change in pressure, a pressure drop, divided by a density and a velocity squared. Could be a half in here for the half g squared, but we don't need it. And this would be defining the Euler number. We know that for kinematic similitude, we require the Reynolds numbers to be the same. So the Reynolds number would be a velocity, a density, and a characteristic dimension. So that characteristic dimension could be the roughness, it could be the diameter, it could be the length. Those are all the choices we have, but it will be, the diameter is the most reasonable one for the things that we're looking at, and divided through by the viscosity. So we said that we should have 4 terms. So 2 of them eat up some of these individual terms, and we're left with some other ones. So you don't necessarily know this, or you shouldn't expect this, but we can look at the remaining terms, and just from knowing what the answer is, I guess, we could define what those other terms would be, and they would be a ratio of length dimensions, length to diameter, and a ratio of roughness, relative roughness. So this is the length to diameter ratio, this is the relative roughness, and so if you see in these terms here, this term comes in. So we can do that by inspection. You could do it by a formal method, like using Buckingham pi, starting from nothing and getting it. And so that allows us to be able to define what these terms are. And so now, if we do some experiments, and so I suppose what we could do, I can probably get it in here. This will actually be equal to the friction factor. So we've talked about that here, this term here. And so if we plot Euler number, which is equal to a pressure drop divided by density of the fluid times divided by v squared, and if we plot a Reynolds number, which is equal to the flow velocity, the density, the length, the diameter of pipe divided through by its viscosity, then what we could do is we could do some tests on a single pipe, I guess, that was of some length and diameter. And that had some roughness attached to it, epsilon. And we could apply a pressure drop to the upstream, going downstream, and we could measure the flow velocity out of here. And so that would give us a value of a pressure drop. It would be water, so we'd have a density. We'd measure the velocity, and so we could have a number for this that would come out of our experiment. I guess this. And we'd measure a velocity, we'd know the density, we know the diameter of our pipe, we know the viscosity of water, 10 to the minus 3 Pascal seconds, so we'd have a Reynolds number as well. So from each of these, we'd have a point. So maybe what we do is we increase the pressure to 2 times delta P, and you get this goes to 2 times the velocity. And so you can do the same for this. We've doubled the pressure. The velocity's doubled, but it's squared, so it's quartered, right? So there's a factor of 4. So we'd expect this number to be lower. And the velocity is increased by 2-fold, so we'd expect this number to be bigger. And so we'd end up with a value. And so the point is that we'd end up with a curve that links these two together. And so we've said already that this Euler number is equal to what we've called a friction factor, which turns up in this expression here. So we've started basically drawing a Moody chart. The first curve we've got 2 points on this. We've got 1 point here, and we've got 1 point here, and we've got the beginnings of a curve that define that. And so that's the mechanism by how we'd figure out exactly what these friction factors are. We do some experiments by typically taking some pipes of different, this is the same pipe, but we're just running flow at different velocities, and we'd find out that we'd get some behavior. Furthermore, if we kept on increasing the pressure, we'd find at some stage that the Euler number would keep on going up, and the Reynolds number would go up, but they no longer would be on a straight line. And so we'd end up finding that we'd get some experiments that started looking like, going off like this. And that kind of define two different regimes. And the two different regimes are manifest in the fact that if you do that on here, if we had a smooth pipe, then this curve goes into this one. So this is very slow flow rates, increasing flow rates, then it goes down on this trajectory. And so the most important thing about this, is that you see two regimes. And these two regimes break at a Reynolds number relative to the diameter of the pipe of about 2000. It's this number here. And that defines the separation between what we'll call laminar flow and the evolution of turbulent flow. And they're fundamentally different. And they're fundamentally different for probably easier to sketch on a diagram like this. They're fundamentally different because if we sketch them on this diagram, then in the laminar regime, if this is Reynolds number and this is friction factor, which is equal to Euler number, then in the laminar regime, which makes a break at about 2000, then the friction factor that we have here is, for a circular pipe anyway, is equal to 64 over the Reynolds number. So it varies as a function of the Reynolds number. But for turbulent flow, the behavior is independent of Reynolds number. So the friction factor is constant for a given roughness. So this is values of relative roughness. And so this would be a rough inside. This would be a very smooth inside. And the key issue is that in this turbulent regime, that it's not a function of Reynolds number anymore. And so that's important to you because in most of the calculations that you'll do, you'll be measuring a head drop within the system. And so once you cancel all the terms out of here, you have a head drop is equal to this. And so if we write this out as the drop in head loss is equal to a friction factor some length over diameter, which we can define, times v squared over 2g. This is the velocity within the pipe. And so if we want to solve this, typically what we'd like to solve is if you know what the head drop is in our system, because you know the upstream level and the downstream level, we'd want to know what the velocity is. So if you want to do that in the turbulent regime, then we know that F equals constant, right? Because these lines are horizontal. So friction factor doesn't change with Reynolds number. It's not a function, so I guess you could also write that as friction factor is not a function of Reynolds number, is the important feature. Then if we want to solve this, then we just rearrange it as v squared is equal to HL times whatever these other terms are. I guess I could do it, right? I won't, well, I'll do it this once. D over L, it would be 2G, and I guess friction factor over here. And so if you want to solve it, you take the square root of both sides, and you end up with a velocity. And so if it's in the turbulent regime, that's exactly what you do, is you end up with a term that friction factor is constant. You can solve it directly, and you come up with a square root of this term, and you end up with this. On this side, the friction factor equals, is not constant. the friction factor is a function of 1 over Reynolds number. For a circular pipe, it's equal to 64 over Reynolds number. And of course, Reynolds number has velocity in it. So the friction factor is going to be equal to 64 over Reynolds number, which is equal to 64 over density, diameter, velocity times viscosity. And so now, when you substitute this expression into here, you will end up with an expression which gives you friction factor has velocity on the bottom, velocity and velocity squared. One of them will cancel out, and you'll just be left with friction velocity on the top. And so you'll end up solving it, and you'll end up, if you rearrange it, you'll end up with velocity is equal to some constant times HL, right? Here you had velocity squared is equal to a constant times HL. Here you have velocity as a constant times HL. So they behave fundamentally differently. So for your purposes, the important thing about these two regimes is that you solve them slightly differently, and there's a different dependence on the velocity in each of the regimes. Pretty straightforward. So these are embodied then, and we'll go through some examples. We've got a week and a half still to spend on this, so we'll go through many examples. But this figure is the one that we'll use, the so-called Moody charts. Moody, I guess you see it down here. Interesting name. And you see that these are functions of the relative roughness. Large relative roughness here, very smooth here. A smooth pipe is this boundary here between them. And I guess you can see that it's not really kind of binary. You don't go suddenly from laminar at 2000 to turbulent as you cross that boundary. There's kind of this transition regime. And so there's a wholly turbulent flow where the friction factor is not a function of Reynolds number and is only a function of roughness. And you have wholly laminar flow where the friction factor is not a function of roughness at all, right? There's nothing that says here anything about roughness. And so if you have your golf ball moving with fluid flow around it in a laminar regime, the drag on that golf ball is not a function of the dimpling on it. It's only a function of the dimpling when you get this regime over here. So that's kind of it. So I suppose we've jumped the gun a little bit in that we've pulled out of a hat the fact that this friction factor, at least in the laminar regime, is equal to 64 over Reynolds number. And so that's kind of been a magic thing that we've done. It's not particularly magic, is it? Of course, you could do that by running experiments, and you could see exactly what the dependency worked out to be. But we will maybe have a go at looking at it slightly differently. If I can go back, don't mean to give you whiplash. Buckingham Pi. The last stuff that we talked about in week 8, before we didn't talk about dimensional analysis, was that we talked about these complicated equations. So if we take the energy equation, resolve it in 3 directions, we get 3 directions for F equals ma in x, y, and z, and conservation of mass. And these are differential equations. They include the effect of viscosity. And what we could do is we could solve these in little differential cubes in the kind of examples we looked at for the lighthouse getting washed over. And we'd solve them because in each of these individual differential cubes, there would be a velocity in x, y, and z, and a pressure. And we have exactly 1, 2, 3 equations and 4. So we have 4 equations that we can use to solve it. The alternative is that we could solve these equations in a very simple geometry, such as flow between 2 parallel plates to represent a duct, or we could modify them a bit to solve them for flow within a pipe, where we apply the appropriate boundary conditions. And the boundary conditions are that the flow velocity at the boundary is 0, and it varies in some form across the section of the pipe. And if we solve them, we'd end up solving one of the momentum equations in the x direction. That's the only one we're left with. And we'd solve a continuity equation for mass rate in equals mass rate out. It ends up being one equation. And as a result of that, we'd end up with an expression that would look something that would be this. And we didn't really go through it, but it says that the average velocity, so the average velocity is if we take this parabolic distribution and we integrate it across the section to see what the area is, and then we just redistribute it as an average value, then this overbar is the average value. And it's a function of the diameter squared, the pressure drop along the length, and the viscosity. And so this is kind of a standard result that we could potentially use to be able to define the magnitude of that. So let's take that and go back to where we were, if I can find out where we were. I wish I could put bookmarks in this somehow, but I'm not smart enough to work that out. And so we've said before that this is the expression that defines the friction factor. So I guess we could derive that. And it's a relatively simple derivation. So we said that the velocity, average velocity, is equal to, and I've got it written down, diameter of the pipe squared divided by 32 times the viscosity of the fluid that's flowing, dp dx, and I guess this would be, this would be L, right? This is the length of our pipe. So this is the geometry that we're looking at. It's no different to the one we've already said something about. This is a velocity, this is a length, this is a diameter. We said that for laminar flow, the roughness doesn't matter, so we don't have to worry about that. I guess we could also utilize the fact that we said before that this pressure drop that we're applying, delta P is equal to HL times unit weight of fluid. And so what we could do is we could substitute this in. And then we know that our standard result is HL is equal to the friction factor. If we just take it from down here, this term here. We didn't derive it, but this is the reality. V squared over 2G. So this again, just to emphasize it, this is the velocity in the pipe, as we know. And so I guess we could rearrange that in some way. So let's rearrange this. So this is going to be HL. So we could write this as velocity. Let's see if I can do this without screwing up. HL. Then this would be 32 mu. It would be length. It would be d squared. It would be delta P is over here. I guess this is unit weight, which is rho g. This term here. Is that about right? Okay. So what else can we do? So we want to get it into this form. So what we could do is I could multiply both sides by V. And then I could try and take out the components that I think are useful. So if this is the case, then V squared over two G. I could use L over D, so I'm not. Whoops, I'll do it here. And that. And hopefully, we should be left with V D rho over mu, and we're left with 2 times 32. Oh God, finally did it right for once. 64. And so this is just equal to 64. This term here is Reynolds number, obviously, times length over diameter times v squared over 2g. So if we have a solution for it, and the solution, this solution here, we should note, is only for laminar flow. In other words, it doesn't allow for the fact that these eddies all come into place as we're going downstream. And so actually, maybe, look at this. I don't think I did it for today, but maybe it was in our stuff from the other day. If I do this, 10.1, yeah. We watched this, and so we spent some time looking at this. This is the idea that we have flow in a pipe. So this would be laminar flow, where it's really just like a pack of cards being skipped across each other. Every laminae of fluid is skidding past itself parallel to each other. And as you increase the velocity, in this case also going downstream, but as you increase the velocity of flow, then this laminar flow ceases to be just skipping over each other, but it has some eddies that develop. And the manifestation of those eddies are across the full length of the pipe. They would be everywhere. You just see their manifestation in the middle because that's the only place where the dye is. But if you move the source of the dye to being closer to the edge, you'd also see these ripples across the edge. In the early part of this flow, if you looked at it, then the velocity profile across this pipe would be 0 velocity here, a maximum in the middle, and 0 velocity at the edge, this parabolic flow. And when you increase the flow velocity and it starts going turbulent, you see these eddies develop, then it would be 0 right at the edge, but as you go a very small amount in from the edge, then it would be the average velocity of the pipe, sometimes going backwards, right? Because if you have turbulent eddies, a portion of the eddy is macroscopically going backwards and some of it's going forwards at the top. And so this is the behavior you're looking at. So the expression that we have is 96 over Reynolds number is applicable only to the behavior that you see at low flow velocities, which is this. Once it transits to becoming turbulent, then it's no longer given by that, and we have to figure out exactly how to do that. And of course, the way you do it would be to apply a pressure upstream, know what your fluid viscosity is, know what your fluid density is, measure the velocity that comes out, and you'd plot it on the Moody chart in terms of your measurements. You'd apply a pressure, you'd measure a velocity, and as you increase the pressure, you get a series of different velocities out of it. And if you plotted those data, you'd end up with a chart that looks like the one we've seen. So I'll get rid of this. So you'd end up with a chart that looks exactly like this. So you take a measurement at a low flow velocity, low pressure would give you a low flow velocity. You take another measurement where you increase the pressure. You take another measurement where you increase the pressure, and at some stage you'd skip over to this curve here. So actually you could think of your individual experiments at different pressures and increasing flow velocities. And if it was an infinitely smooth pipe, you'd keep on going down here. These would be the measurements you'd make. I guess that's probably pretty smooth, that pipe we just saw. It's plexiglass. But if your pipe had some roughness on the inside, then you'd skip down here, and then you'd skip across on one of these curves. And you'd find that when you got to being very high flow rates, flow velocities, then the magnitude of this friction coefficient reaches a constant, and it should, and if you can measure it on your model, then you'd know that the data that you have for this curve represents a certain friction, a certain roughness, and therefore you have it. So that's kind of it. So that's really what the essence of pipe flow is. So that's, I guess, how you'd construct these charts. We're not so interested in constructing these charts, but we're interested in using them. And so we're interested in using them, so we're interested in being able to do the first part of this. We'd like to draw our system. We'd like to realize whether we have a pump in here that's providing head or not. If there's no pump head in the system, then the pressure drop, head drop between upstream and downstream has to be made up for by the frictional losses in this pipe. And if we write Bernoulli between locations 3 and 4, we end up defining that they're equivalent, right? The pressure drop between 3 and 4, if it's just a static column of water in each case, is exactly equal to the elevation drop between those two surfaces. And so this factor applies. We want to know what this value is, or if we apply this value, we want to know what the velocity is. If we know what this is in our system, we know the length of our pipe, we know the diameter of the pipe, we know how rough it is, so we might know the friction factor, then we can figure out the velocity. The only trick comes is that sometimes the friction factor is a function of the Reynolds number, which is a function of the velocity. So we can't always solve it in one step. And so the mechanisms that I mentioned here that differ between whether we're laminar or turbulent, we have to mess around with a little bit and understand that. So we'll talk about some ultimately different quote-unquote types of problems. Type 1, Type 2, and Type 3 problems. Type 1 is the easiest. Type 1 is where you're told that the velocity in the pipe is equal to 1 meter a second, and you have to calculate the head loss. It's easiest because if you know what the velocity is, you absolutely know uniquely what the friction factor is, because you have a Reynolds number that you know because you know velocity. And so as a geometry of the pipe, you absolutely know what the friction factor is, and you can solve it in one step. But if you want to be able to figure out exactly what the diameter of the pipe is to give you a particular flow velocity with a given head loss, then you don't know what the flow velocity is, and so you have to iterate to a solution. So it just gets to be a bit more messy, but ultimately solvable. So from now on in, we'll talk about using Moody charts, and I guess I didn't really talk about this, but we did say there are two things. There are major losses, which are due to the drag in the pipe, which we've spent most of today talking about, and there are also minor losses, so that if you have a bend in your pipe, whoops, I didn't even do that. It sees both my finger and my thing. So if you had a bend, multiple bends in this pipe as it goes down here, you just have to add these individual losses. And we can calculate those losses as a function of the kind of pipe we have. And so not surprisingly, well, just defining this is just defining the equivalent roughness as a function of a diameter of pipe and the type of pipe, nothing more than that. So it's just, this is a pipe that has a given roughness, so as a function of diameter, you'd expect the relative roughness to scale. It's just multiplying. This is just a normal graph to define those. Not particularly interesting. So what we'll do next time is we'll talk about using these to solve problems, and we'll do, ultimately we're moving towards, if I find it, it doesn't matter, a table, I can't find it, that talks about type 1, type 2, and type 3 problems. And the only issue is that the easiest problem to solve is if we have a defined velocity, we know the Reynolds number, we know the roughness, we can solve for the head loss. One step. If we want to dimension pipes for a given velocity or a given capacity and a given head loss, then we just have to assume initial velocity, check if it's right, check if it's the right Reynolds number, see what the friction factor is if that Reynolds number, and then iterate between them. So that's it. So we'll do that coming on from here. So that's it. Okay? Questions? Yes?
Would you suggest that we find one of those many graphs we have?
Yeah, there will be two questions on the test, and they will be pipe questions, and you'll need Moody charts for one of them. But the review session's already online as of yesterday, and so, but you have them accessible anyway, right? Because you have everything available.
Right.
There is one in the test, but it's not a very high definition one.
Perfect. Thank you.
No problem. Okay. All right, great. Have a great Wednesday, whatever day it is today.